Hi, my name is Dr. Harvey Miller, and welcome to another installment in our course on operations management at the Sobi School of Business at St. Mary's University. This particular topic is called inventory management, and inventory management is a very important topic because in the production of goods and services, we often have to have inventory of either finished goods or goods that are work in progress. How do we manage inventory so that we ensure that we can deliver either the products or the services that we promise our customers in an efficient and timely and cost effective fashion? So that requires management of inventory. So we're going to explore this particular topic and learn about a few things. We're going to learn about what types of inventory exists and the role of those different types of inventory. Also, we'll talk about how do we classify inventory so that we could focus on what's most important when we're managing inventory. It's very important to keep an accurate count of the inventory that you have because it is often a significant investment, financial investment, and so therefore inventory accuracy is also very important. Then we will first start to focus on the two key decisions that we have to make when we're managing inventory. One is called when to order, and the other one is how much to order. So we require inventory for either as finished goods or as parts of a larger product, in which case we're talking about components. And there is the question of when we are trying to satisfy the demand, just how large our inventory investments ought to be every time we place an order for inventory items. If we place an order that's too large, we may have a lot of investment capital tied up in inventory that could cost us. If we place an order that's too small, we could run out of stock and lose a sale. All right, so we have to get it just right. And then, of course, how often do we order? When do we place the orders? Once every 2 weeks, once every 3 weeks, once every 4 weeks. So the combination of these two questions is really what we're going to be focusing on in this particular chapter. So what is the fundamental objective behind managing inventory? It is really to strike a balance between meeting the customer's expectations, so in other words, providing customer service, and also managing our investment in inventory, all right? We need to make sure that we manage the investment in inventory. You don't want to have too much capital tied up in inventory. So balancing those two things is really what inventory management is all about. Why is it so important? It's so important because, as I mentioned to you, inventory management or inventory represents a significant investment. It's usually an asset, but could also be viewed as a liability, but it's an expensive asset. And if we fail to sell it, move it to its final destination, then it becomes a cost on the organization and therefore a liability. In some cases, inventory can cost almost up to 50% of the total invested capital. If you think about selling, say, for example, fresh produce, the actual raw material cost of that fresh produce itself, and the cost of acquiring that before you sell it to a customer, before you add the margin to it. So if you're going to add a 10% margin or 15% margin, that means that the bulk of the cost has to do with the actual raw material itself plus the supply chain related costs. And all of that is part of the inventory costs. It's made up of a combination of factors. All right. So as you mentioned, it's important because there's a need for operations managers to manage the balance between customer service and the inventory investment. So there are functions, many functions that inventory play in an operation system. One very important function is to decouple the various parts of the production process. So if you think about, say, manufacturing and distribution, two components right here. If you're manufacturing here and you're distributing here, in the middle, you might want to store some inventory, in which case we call those buffer stocks. Imagine if there were no buffer stocks. If the manufacturing system breaks down, then it means that you have no inventory at your distribution centers. And then if there's a demand that comes to the distribution center, it will not be filled. So therefore you'll have a shortage. But if you actually stored inventory at the distribution center, if there's an issue with the manufacturing facility, the distribution center can still satisfy customers' requirements. And so therefore inventory, the fact that you have inventory at the distribution center or in the pipeline between manufacturing and distribution can help you hedge against any demand that happens through the distribution center. All right. The other reason why inventory can or role that inventory can play is to decouple the firm from fluctuations in demand and provide a stock of goods that will provide a selection for customers. What we're saying is that demand fluctuates. I mean, if demand was very steady and constant over time, if that was demand, then you just need, that it's very easy to satisfy the demand. But if demand is varying over time, you have to, so you have to then have some inventory in place. So if you say, well, let's just keep an average amount of stock, then as you could see, what would happen is in this case, here you would have inventory over here. It looks like you may have a shortage over here, but you would be storing some inventory. But this inventory in the first period here can satisfy the excess demand in that second period. This is 1, this is 2, 3, and 4. All right? But you have to really make sure that you balance your production in such a way that you have inventory to allow for fluctuations in demand. All right? So that's another important function of inventory. Sometimes, if you want to take advantage of quantity discounts, it may require that you incur inventory. What do we mean by that? It's because if your needs are, let's say, 500 units per month, if you could just order, and that was constant, if you could just order 500 units each month, then you wouldn't carry any inventory. However, if the manufacturer says, if you order 1,000, however, I will give you a 10% discount on the price of each item. You want to save that 10% because then if you then turn around and sell the goods, that 10% accrues to you, the retailer. So what do? You say, okay, I'll take 1,000, but you only need 500 in that particular period, in that month. So therefore, you're going to have to carry 500 units of inventory for the next period. So sometimes in taking advantage of quantity discounts, you could end up carrying inventory. And of course, to hedge against inflation. If prices are likely to increase, if we only knew that the price is associated with goods and services were going to increase after COVID, maybe a lot of us would have done different things prior to COVID. Construction materials went up significantly. Almost 40 to 50%. And so if you had a renovation project to do prior to COVID, you would have said, oh my God, I should have done it prior to that. So in which case you would have been hedging. You might have bought all of the materials before, even though you may not have been ready for your renovation. And that material will be sitting there, well, that's inventory. And then you have capital tied up in that inventory. But because you're anticipating some inflation, you decided to incur some inventory costs so that you could hedge against the inflationary price associated with the items. All right? Types of inventory, raw materials, of course, that goes into the production of goods. Work in process is what happens between two facilities. So if you have a workstation 1 and 2, raw materials might come in here, raw materials, and then work in process inventory is what goes in here, because you probably have an assembly process. Maybe that has, I'm just saying, let's say 3 steps. So you're carrying some work in process inventory in between those two. You may also carry some work in process inventory in between 2 and 3. All right. So work that has undergone some changes but has not completed yet. Then you also have maintenance and repair, MRO, inventory. So spare parts, for example. And then the actual finished goods, when you produce the product, at the end, finished goods inventory. All right. So then that's what's actually sent to either your distributor or your retailer, and then goes to your customers. All right. If there's a distributor, then the distributor would have a retailer as a customer. If there's a retailer, the retailer would have the end user as the customer. So all of these different types of inventory, they have different costs, they have different functions. This is an example of a flow of material, and you can see at each of these stages there, this really represents different types of inventory. So your raw material input into a company that is making perhaps paper, I believe that is, or wood blocks, and then you have to wait for inspection, then it's moved, then it's taken over to the facility where it's going to be cut. Then you actually do the cutting and here. So even when the item is actually sitting here, that's raw materials, right? It hasn't undergone any processing yet, but now it's finally processed. This may actually be the finished good, or it could be a work in process inventory that goes to another stage. But since this is the actual output according to this flow diagram, then this is finished goods in this case. All right. Let's talk a little bit about managing inventory. If you're going to talk about managing inventory, then we need to focus on classifying it, because if we're able to classify the inventory, it might make it a little bit easier for us to manage it. And also, how accurate are inventory records? Because if you're going to make a promise to customers, you need to be able to promise on the basis that you know exactly what's in stock. A lot of retail companies may show items online only for when you place the order to be told that the item is back ordered. And that's because there's been a lag in the updating of that system that is supposed to show what the actual inventory level really is. So inventory accuracy is extremely important, because you could lose business that way. So let's talk a little bit about ABC analysis, what's involved. With ABC analysis, what we're doing is we're dividing our products into 3 categories, A being the most important, B second, and then C the third. But to classify them, you need a system of classification, and you could do so on the basis of what we call the annual dollar volume that is contributed. And we use a sort of a 20, 30, 50 kind of a percent rule, in that we'll take the 20% of the items that is at the top 20% in terms of contribution, and we'll call those A items, most important. Then the next 30% we will call those the B items, and 50% the C items. And how we manage those are very important. Now, in the past, before we had point of sale systems that allowed us to see inventory levels, daily and on a continuous basis in real time, we had to physically inspect inventory. And so that is why there was a need for classification. So by then coming up with the ABC system, we would actually give the most attention to A items, which was 20% of your overall annual volume, either sales or costs or whatever you want to use. And then we will have an intermediate amount of attention paid to your B items and the least attention to your C items. So here you could order what we call, you'd monitor the inventory until it gets down to what we call a reorder point, and then place the order. Whereas B items, you might actually do periodic order quantity, a periodic order, which means that you monitor, but maybe once every couple of days you take a look at the inventory, and then C items could be, well, we order enough for 6 months. We don't have to look at the inventory level until maybe the fifth month to see where we are, and so the least amount of attention to those. So relatively cheap items are what you would use for this. Here's an example of a problem right here. We have a number of items, and we have their stock numbers, and then we've done our calculations, and based on the we've done, we have the annual volume in terms of units that are sold. We have the unit cost, and therefore we could compute the annual dollar volume. So 1,000 times $90 gives us $90,000, and so on. Once we've computed our annual dollar volume, then what we do is we now arrange the annual dollar volume in descending order. So 90, 77, 26, 15, 12, right? So you look at those values, and if I go to the next page, you'll see the balance: 8,000, 1,200, 850, 504, 150. All right? So if we have all of this on one page, it'll be easier to see. So there are 10 items in this case, so we will take the first two, and the first two basically accounts for 72%, as you can see, of the total annual dollar volume. Then the next three accounts for 23%, and then so that's what? That's 95. So the last five is going to be accounting for only 5% of the total volume, sales volume. So as you can see, we won't treat those as necessarily the most important category. All right, least amount of attention. Let's see items, most amount of attention. This idea of the 20% really is kind of linked to the 20-80 rule, which is that 20% of the items will contribute approximately 80% of your value. In this case, it wasn't exactly 80%, it was 72. But the idea is that really a small number of items will contribute the biggest chunk. So let's focus on that small, the vital few, and then let's kind of reduce our level of attention on the others that remain. So the process for handling this is to first compute what your annual value is, contribution for each item. Then you arrange it in descending order. And what you then do is look for your sort of a 20, 30, 50% cutoffs. If you have 10 items, then the first two is 20%. If you have 20 items, then the first four, and so on. All right? And that's what we would use. Now, this is just a graph that shows you what we're looking at in terms of A items, B items, and your C items right there. If we look at the criteria in the last example I just showed you, we use what we call the annual dollar value, right? Contribution or volume. Sometimes you could just do it on the basis of volume, in terms of the actual value, but you have to be very careful that there are some cases, some parts that are very low in value, right? Can be extremely important, you know? So for example, imagine if you have a bolt. If you have a bolt that is important for an engine, right? That bolt might only cost you 50 cents. But if you don't have that bolt, imagine that if you're talking about an aircraft, then that means that the aircraft cannot move. And we know that the value that the aircraft contributes, or on a daily basis, the cost of operating an aircraft is extremely expensive. Or the contribution that it can make to the profitability of the firm is significant. So without that 50-cent bolt, you could actually impact the costs or the revenues of that airline. So in that case, that 50-cent bolt is extremely important, even though its dollar value is actually low. So it means that you have to find other criteria when you're classifying inventory, not just cost or revenues, all right? So you see here that other criteria other than annual dollar volume can be used based on anticipated engineering changes, maybe that might happen. So if a part is necessary for that, then they're going to make that important. If you have some delivery challenges, and so there may be some items based on the challenges that you face, you want to prioritize them based on quality challenges or based on the unit production costs. All right. So what are some of the policies that you may employ when you are looking at ABC analysis in terms of the classification of the inventory based on the level of importance? Place more emphasis on supplier development for A items. So if the A items you've classified are critical, then of course build a really good relationship with your suppliers. And then if you have the resources, focus on supplier development so that way you have greater reliability and a stronger loyalty from that particular supplier. You also have to have tighter inventory control because falling short of those A items can have significant implications for the organization. And then you have to also be careful in terms of your forecast. You want to improve your forecast accuracy. Now, keeping accurate inventory records is something that's very important if you want to avoid shortages. Excuse me. But not only shortages, but you also want to avoid excess inventory because it may be fairly costly. So accurate records are critical in production and inventory systems. So the organization can focus on what's needed by ensuring that it knows exactly what it has in stock. It's necessary to make precise decisions about ordering, scheduling, and shipping. Again, why? Because if you have inaccurate inventory, you might preemptively, or I should say prematurely, place an order when you didn't have to. Or you might very well find yourself placing an order too late because you thought you had an item in stock, but it's not in stock. And so therefore it should have been ordered. So having precise, a precise count of what your inventory levels are is critical to that. And of course, it's important for your financial accounting purposes to know the value of inventory you have in stock, because if it is too expensive, then you might need to focus on how you lower the costs associated with your inventory. So cycle counting is a strategy for assisting organizations in terms of developing accurate records. In the past, when companies wanted to kind of really bring their inventory levels up to date in terms of the accuracy of their counts, they used to literally shut down the business on a weekend and then invite their workers to come in, have to pay them overtime, and do counts. And so they would have all the employees counting parts of the warehouse or parts of the goods on the floor. But rather than doing that, cycle counting is a tool that can be used that prevents the need for these sorts of shutdowns. So what it is that if you have a large number of SKUs, say for example 1,000 stock keeping units, we call them SKUs, then what you will do is you will actually use your classification system. And if you now have, say for example, your ABC system, then the 20% of these items, in that case 200 of them, you will determine, well, because they're critical, I want to count them say 6 times a year. All right? So if you want to count them 6 times a year, that's essentially 6 by 200, 1,200 item counts. And then if you now say, well, we have 300 days per year, working days per year, then 3 into 12 is 4. So on a daily basis, you will count 4 items. All right? You'll count 4 items, and if you repeat the next set of 4 items, 4 items, 4 items, 4 items, 4 items, 4 items, you and then when you finish, when you get to 200, you repeat the cycle. That's why it's called cycle counting. You will get to count each item 6 times per year. All right. Now, counting 4 items per day is a whole lot easier than shutting down your business just to count 200 items in one morning. All right. So that's the basic idea behind cycle counting. You take the items, you know the number of counts you want per year, determine the total number of item counts, divided by the number of days in a year, and you know how many items you should be counting. Now, if it turns out you have a large number of items that you're counting per, because if you have several thousand stock keeping units, but once you determine your daily count, you now could allocate that to your staff members. And then when you count is also important. You want to count when your staff are fresh. So usually, you get some staff members who are going to be put on counting duty to come in early in the morning before the business gets busy, and then that way the counts can be done, right? Early. So items are counted and it's updated on a periodic basis, often using ABC analysis to determine the cycles. I just showed you how by using ABC analysis here, we would then say that if we wanted A items to get 6 counts, then that would be 1,200 item counts divided by 300 days. So the next study, which is 300 items, for example, if we only wanted those count 3 times a year, so what will happen is 3 by 3 is 900 item counts divided by 300 days. So in that case, we would count 3 of them per day. All right? 3 of those per day. And if we keep repeating that, then the B items would be counted 3 times per year, compared to A items is 6 times per year. And then for C items, you might say you only want to count it once, right? Per year. So just some of the advantages of doing cycle counting: eliminates the need for shutdowns and interruptions, eliminate the annual inventory adjustment, because if you keep updating your inventory levels on a continuous basis, you don't have to at the end of the year say, oh, we need to shut down, count, and so that we could update our inventory records. You basically have trained personnel audit your inventory, allows causes of errors to be identified and corrected. In other words, you don't have to wait till the end of the year. If, as you're starting your cycle counting process, you discover there are some problems with your system, either your storage system, your management system, your information system, you can correct that early, okay? And then it helps you maintain accurate inventory records. So what about service inventories? Because often when we think about inventory management, we think about manufacturing environments, but the reality is that we have items in both services and manufacturing. So the inventory can be a critical component of profitability. Losses may come from shrinkage or pilferage. And then we have applicable techniques include good personnel selection, training and discipline, tight control of incoming shipments, and effective control on all goods leaving the facility. So, but also, given the nature of the service that you're providing, then, you will have to really understand the demand for your service and then translate that into the demand for what I call the facilitating goods, the goods that are necessary for the service. So if you have a car rental company, for example, then your inventory of cars available for rental will come from your forecast. And then so the car is a facilitating good by providing that service. The service is to enable someone to be able to have access to automotive service at the leisure and flexibility, and to be able to do that, you have to have a fleet of cars available to rent. Okay, if you're thinking about in disaster areas where we have warehouses, and if we want to move food to citizens, then the same thing, we have to be able to forecast the demand for food, and then we would have to have sufficient stockpiles of food to be able to feed the hungry. All right? So that happened in food banks, or just disaster relief and so on. Some cases when you have hurricanes, people need shelter, people need clothes. So again, forecasting is also important in that part. So now let's talk about, managing inventory using techniques and tools or models. It's important to note that there are two broad categories of inventory when we are thinking about the kinds of tools that we use. One set that we refer to as independent inventory, and the other set that we refer to as dependent inventory. So independent inventory would just be your finished good items. At the end of the, what we stock in the retail facility or in the warehouse, it is an item that you would sell to a consumer, right? And that item does not depend on any other set of items. It is independent of others. However, there is something called dependent demand, where if I am actually making a product through an assembly of different components, so that's my product, component 1, component 2, component 3, and then I require 1, I require 2 here, and I require 4. So if my demand for my final product is 10, it means I will need 10 of C1, right? I will need 20, and then I will need 40. So the demand for these items, components, is dependent on the demand for the finished good. All right, and so that's why we refer to this dependent demand. When we imagine managing inventory, part of it is, as we said, is to balance your cost of investment versus the service. To achieve the service, the more inventory will allow you to achieve the service. However, more inventory will allow you to incur costs, which you want to try to minimize. And so therefore, we need to understand what are the main cost components when you're managing inventory. Holding cost is one of them, the cost of carrying in the inventory over time. So if, for example, if I had $100 and I bought an item and I held it in inventory, the cost of holding this for a year, we will say, would be at the very least equivalent to or greater than if I had put this money in the bank. So if I was going to get maybe a 10% interest, right, from the bank, then 10% of 100 per year would be $10. So the cost of carrying that item would be at least $10. But often, if you have this item in a warehouse, well, guess what? You have to have electricity, water, other maintenance. These are all like a number of costs that are related to utilities and maintenance. All right? So it would not just be the $10, it would be $10 plus these additional costs. Sometimes you have to include insurance. If there's transportation, there's the risk of pilferage, there's the risk of breakage. A certain percentage of the item might get broken. So you have to factor all of these things in that, okay? Now, the question of when do we place the order? There is something called an economic order quantity that we will learn about, which basically means that that quantity that we order will give us the best cost. There's another model called the production order quantity, and then there's a quantity discount model. All of these three focus on the decision on what is the optimum quantity to order, Q star. And so the most popular of these models is the basic EOQ model that we will take a look at very quickly. There are a number of assumptions associated with the EOQ model. It assumes demand is known, that the lead time is known and constant. So if I place an order for an item, if the lead time is 3 days, every 3 days it will, if I place it in 3 days exactly, the item would arrive, right? The receipt of the inventory is instantaneous and complete. There are no losses, there are no breakages. We don't have any quantity discounts. The only variable costs are set up on holding costs. And then stockouts can be avoided because why? Because the demand is known and independent and it does not change. So in that case, we could show how our inventory is used over time. The inventory is used over time by, first of all, starting off with a quantity right here. And because the demand rate is constant, let me just go over red, we will use it at a constant rate. When it arrives at 0, we will receive inventory instantaneously. A lump of, a big bunch, quantity of inventory Q star, Q, which is our optimum, which is our other quantity, will arrive. Of course, to determine when you place the order, you'd have to know something about the lead time. So if the lead time LT is this period right here, between here and here, it would mean that you place your order right here. We call that the reorder point. Because when the inventory gets to that level, the inventory gets to the reorder point level, you place the order and it will arrive in this period right here. And this would be the same. Now granted, this is just, it just happens to line up with the dotted line over here, but that's just a coincidence. Lead time. And, sorry, lead time. All right, so that's our reorder point right here. So the average amount of inventory that we would end up having for each cycle, each of those we refer to them as a cycle. So the total amount ordered is Q. The rate at which we use it is the slope of that triangle that I just showed you here as a usage. Okay, and then we have a lead time that is fixed. And so if you think about what's the average amount of inventory that we carry, if we start off with Q and we end with 0, and we take the average of this 2 is Q over 2. That's where this comes from in terms of the average amount of inventory. So the model basically says, okay, we have average inventory. I'm going to pay, my total cost is going to be ordering costs. Well, if my annual demand is D, and my order quantity is Q, that's the number of orders that I would place per year, is D over Q. Easy to understand. If I have an annual demand of 1,000 units and my order is 100 units per order, then I will order 10 times. And so my costs associated with ordering inventory is S, which is the setup cost or the ordering cost, times the number of orders. And then I'm paying inventory carrying costs, annual inventory carry, on the average amount of inventory I am holding, which is Q over 2, times H. So H is your annual holding costs. S is your ordering costs. So given that I have this function, essentially I want to determine how I could get what order quantity Q star would minimize this function for me. So I want to minimize my total annual cost, right? If you were to draw this diagram, what you will find is that your holding cost, as your order quantity increases, Q, your holding cost is like this, but then your carrying cost gets lower. And so if we bring those two costs together, there's an optimum quantity Q star. So we want to find that. And so to be able to find that, we would actually end up using a little bit of calculus, where we are going to find the slope of this line, equate it to 0, and find the value of Q that is equal to. So you're going to have to take DTC, or total cost, over DTC over DQ. Let me just do this again. You would have to equate D total cost over DQ, right, and equate that to 0. That's the calculus, the differential of this function relative to Q. All right. So without going into all the calculus and everything, we actually end up with an equation, and that equation is given to us here. So basically what I've shown you there, just allow me to skip all of these things here. So this is what the graph looks like that I just showed you. All right here. So this is cost. And as you can see, the curve, the cost per unit, in terms of the setup cost per unit, decreases as your order quantity increases, but your carrying cost actually increases. All right. And then this is just to give you the nomenclature, number of orders, pieces per order, or your order quantity, your annual demand, your setup cost or ordering cost, your holding cost per year, and then of course this is your optimum quantity. I just showed you that this was the ordering cost, and then there's the carrying cost, right? Take Q over 2 times H, and when we bring the two together and we do our calculus, we will get Q star, the optimum order quantity, is equal to the square root of 2 times the demand times the setup or ordering cost divided by H. All right? That's what that is right here. So if we want to do a very simple example, you could certainly do that. You could say if we have annual demand is equal to 5,000, our ordering cost is $100. Our holding cost is $10 per year, right? And then what is our optimum order quantity? So Q star will just be equal to the square root of 2 times 5,000 times S 100 over 10. So if I work this out a little bit, that becomes 10 times 50,000, so the square root of 100,000. Right? I believe that's what that is. 50 to 100. That's right. 10, 50,000 times to 100,000. So what is the square root of 100,000? That will give us our Q star. So 100 by 100 is actually 10,000. So this is not quite I don't have my calculator with me, but you could actually find what that answer is. So that's essentially how you would go ahead and compute this, all right? What do we know about the EOQ model? One of the things about the EOQ model is it's extremely robust, and the reason why it's robust, meaning that if we just fare slightly off of Q star, the optimum quantity, the cost does not increase significantly. And I'll tell you why that is because it turns out that where the optimum order quantity is, that area is reasonably flat. So if you have a quantity here, or a quantity here, or quantity here, there's very little difference between those. So that's why it's considered a fairly robust model. Okay? All right, so I'm not sure at what point I lost my visual, but I will take a look at it again. But just perhaps so we could go through this section right here. I'll just remind you of the EOQ model, which basically is an optimum order quantity model that attempts to balance the total ordering costs with the total inventory carrying costs. And as I mentioned, the total cost is the annual demand divided by the quantity to tell us how many orders times S, the unit costs every time we place an order, plus the average inventory. If we start off with Q and end with 0 divided by 2, we'll get Q over 2 times H. So the function that this represents, okay, here we go again. I'm losing my, my diagram. The function that we represent here is what is this sort of a convex function, and we just find the minimum of that particular function, all right? So I explained a little bit earlier, and I may have lost the visual at that point in time, but these are the, that's the nomenclature. Q is the number of pieces per order, Q star is the optimum order quantity, D is the annual demand, S is the set of costs, H is the annual holding cost. All right? And so I've just shown you how we will calculate all of the parts, which is the ordering cost and the holding costs, and simply solve for Q star when we find the sort of minimum of that function. In other words, we use some calculus. When we find the minimum of the function, it gives us that the optimum order quantity Q star is the square root of 2 times the demand times the ordering costs over the holding costs. All right? And then I was just sort of showing you this example where if your annual demand was 5,000 units, and S, which is your holding cost, is $100 every time you place an order, annual cost per year is $10 per year. Then our optimum order quantity will be 2 times our demand, 5,000, times our ordering cost, 100, divided by our holding cost per year. Sometimes we express the holding cost as a percentage of the price of the item. So we could have this as basically I, the interest rate, times the unit price of the item, or the unit cost of the item, of producing the item. All right. For this example, our answer would just be the square root of 100,000, whatever that turns out to be. And we sort of work with that, okay? Just to finalize things, I was speaking about the idea that the EOQ model is fairly robust because of the fact that right here at the point where we have the minimum, the curve is fairly flat right here. And so varying the quantity, the order quantity in a range right around the minimum is not going to have any significant impact on the cost. It's relatively flat in the area of the EOQ. All right, now the question of when we actually place the order, the reorder point, is essentially just the inventory level at which we're able to place the order and receive it just in time before we actually run out of stock. So if this is our inventory cycle, and remember everything is constant, right? It's known. So what happens is that if we know our lead time is this period right here, our lead time, Then if we go across, this becomes our reorder point. When the inventory level gets down to here, we place the order, right? And then the item will arrive here and replenish the stock. And then the process repeats itself. So this will always be the reorder point right here. So what is that reorder point? If you think about it, it's the rate at which you use demand, this piece right here, times the lead time in days or whatever it is. So if I'm using the demand at a rate D units per day, and my lead time is LT units, days, sorry, LT days, then my reorder point will just be my average demand, or my demand during the lead time, because that's the period you're trying to cover. Essentially, your reorder point covers the demand while you're waiting to receive the stock. So I need to know if my usage is 5 units per day, and it's going to take me 3 days for the order to arrive, then 5 times 3 is 15. I should have 15 units available, and so that when the item arrives, it's just about 0, but it replenishes me back to the order quantity queue. All right? So the formula for reorder point is relatively straightforward. Your reorder point is your demand during the lead time times your lead time. Okay? And that's assuming that everything is known and constant, there's no variability. However, if there is variability in the demand, we now have to have what we call safety stock. And the safety stock is the quantity that you keep to allow you to address the fluctuations in the demand while you're waiting for your product to arrive during the lead time. Okay? So we will actually face that a little bit later. So this diagram is just showing you exactly what I've already shown you, which we have the usage, the reorder point, and then we see the lead time right here. So that's our reorder point in units. And we will place the order at the to give us just enough time for the item to arrive. So D is your average daily usage, which would be your annual demand divided by your number of working days per year. And then, so in this example, we have 8,000 iPods per year, 250 working days per year, lead time is 3 working days. So compute that and then bring it down to a daily demand, which it turns out to be 32 units per day is what you're selling. And then if your reorder point, so lead time is 3 days, you multiply by 3, and that will give you your reorder point. So 96 units is what you must have on hand when you place the order for the item. Okay? Production order quantity model is a slightly different model, and we will talk about that a bit more later, but let's just understand what it means. This is a case where you are building inventory and using it at the same time. You're building inventory and using it at the same time. And so instead of the sort of standard EOQ model, where things are instantaneous, in this case, it's a little different. What would happen is that instead of things being instantaneous, I'll show you the modification that we have to make, is that now we will not acquire the inventory instantaneously, but we're going to build the inventory at a rate. And then the inventory gets used. Then we got to build it again, then it gets used. We build it again, then it gets used. So when we say build it, we're producing. So if you're producing, say 5 units per day, then it might take you so many days to build the inventory, right, until you get to your quantity or the quantity. then you will continue to use the inventory until you then start production again, and then you build it up. So that's the difference between the production quantity model and the EOQ model. To give you a sort of a funny way of thinking about it, right? Let's say if we were making cookies. If we were just making cookies, and every time we place an order for cookies, we will get 50 cookies in batches, right? We're getting the cookies in batches. So here's a case now. We'll say, okay, I'm going to actually be making cookies. I could make it, I could make, say, 20 cookies per minute or whatever. Not, well, whatever, let's not say no minutes. Let's say I can make, 20 cookies per, let's just use minutes for now. So what happens now, it might take you, if you were looking for a batch of 50, it would take you, that's what, 2.5 minutes to get the 50 cookies and so on, which just sounds kind of crazy because the cookies have to cook. But let's just follow me for a second. What if when the cookies come out of the oven, as you're making the cookies, you're using them, maybe you're eating a few. So you're making batches of 20, right? But then you're eating 5, per minute. So what happens is that in any given period of time, you're producing, but then you are using some of your inventory. So at the end of the production period, you're not going to have what you set out to produce. So if I'm going to make, let's say, if I'm making 20 cookies per minute, but I'm consuming 5 of them per minute, it means that I am going to have 15 cookies at the end of that minute. So I am accumulating cookies at a rate of 15 per minute, not 20, because I'm consuming time. So why is this kind of model relevant? In some manufacturing environments, the products that you're making, particularly when you're making components, are being used at the same time you're making them. So if we're making bicycles and we're making handlebars, for example, that part of a bike. So what happens is as we're producing the handles, some of what we're producing is actually going to be used in assembly at the same time. So you may find a worker coming and taking a small batch of handles and then taking it to another workstation to assemble while we're producing a batch. So P then becomes your production rate U becomes your usage rate or demand rate. Let's call it the usage rate. So therefore you will accumulate at P minus D, right? And so P must be greater than D. You cannot use at a greater rate than you're producing. P must be greater than D. So it will actually give us a unique EOQ model, or when I should say EOQ, a unique model that allows us to determine the production order quantity, recognizing that we're going to be using some of it at the same time. What it actually does, it really forces us to produce more than we would have if we just had an EOQ model. So that model will be shown to you in a subsequent video, okay? So to summarize, inventory represents a major investment for many firms. There are 4 types of inventories: raw material and purchase components, work in process, maintenance items, repair and operating items, finished goods. There are many methodologies for calculating the best just-in-time inventory requirements, mathematical techniques, including the use of Excel and other software, is frequently used in computing the economic order quantities. Or remember also too, there are 2 main decisions that we make, which is how much to order and when to place the order. How much to order is the order quantity, Q star for EOQ. And then if we're looking at production order quantity model, then there is the optimum quantity, but we just call it the optimum production order quantity, POQ. And the decision of when to place the order depends on your lead time, which is basically the average demand during the lead time multiplied by the length of the lead time itself. In the case where there is no uncertainty, the reorder point is simply the demand multiplied by the lead time. The daily demand multiplied by the lead time in days, or the annual demand multiplied by the lead time in years. Well, just make sure that the units are consistent, all right? So that will bring us to the end of this video, and then we will go to part 2, where we understand a bit more of some of the other inventory management models.